Okay, in this video, we're going to continue to talk about the ground reaction force. And now we're going to use a movement where we're going to squat from a standing position to a lower position. And I'm really going to deal with just the vertical movement for this type of task. So I've just drawn a couple of stick figures here so we can see this and talk about it a little bit. Here I've got standing at time 1, and then in the lower position, squatted down position, in some time later. So we went from this movement downward, and so this is time 1, and this is some time later. I've got the center of mass identified here. So let's identify forces acting on the object, given our kinetic analysis approach. What forces are acting on the object? Well, I have Fg pulling downward on the person, and I've got FGRF pushing up on the person. Okay, those two forces. And those two forces exist over here. Fg is the same magnitude over here, and I've got FGRF here as well. And what I want to do is really try to understand this ground reaction force magnitude during a squat maneuver. And what we'll see is that these two forces are not always equal to each other, but these are the two forces acting on the object. And again, we are not identifying putting forces created by the person into this kinetic analysis approach. I do want to understand the forces created by the person, but what we'll see is that those forces are reflected in the ground reaction force. This ground reaction force is in reaction to what the person's doing. Okay, so let's continue our kinetic analysis here. We take these forces acting on the object and we put them into this equation, and we understand the product of mass of the person, measure of an object's inertia, times the acceleration due to the center of, acceleration of the center of mass of the person. Okay, so really I need to just think about what's happening to the center of mass of the person during this movement. I'm not looking at specifically how the arms are moving, how the trunk is moving, how any segment's moving. I'm looking at collectively the center of mass, how that is moving during this task. Okay, we take these forces acting on the object and we get the product of mass times acceleration of center mass. So I'm going to put them into this equation here, and I'll jump ahead, only considering the vertical movement here. I'm not concerning myself with the horizontal movement. So I have the ground reaction force, ground reaction force plus force of gravity. That's negative because up is positive. And that's our standard reference frame for our kinematics and kinetics. Up is positive, so gravity is pulling down on the person. Ground reaction force is pushing up on the person. We add those up and we get ma. Or I'm going to rewrite this equation. Either of these is fine. The ground reaction force is equal to the product of mass and acceleration of the center of mass and gravity. All right, so now we can see if we have acceleration of the center mass, these two forces, force of gravity and force of the ground pushing up on the person, are not equal in magnitude. Going back to the previous video that you should have watched, I emphasized that when standing still, these two forces are equal in magnitude, and they happen to be opposite in direction. But that is a situation where there's no acceleration. And this equality sign is true when there's a zero acceleration. If there's a change in velocity, which we'll see in a second, and there is an acceleration, these two forces are not equal and opposite, as not Newton's third law. Only forces acting on the object enter this equation. So what I really want to do in this video is understand the acceleration of the center mass. If we can understand the acceleration of the center mass during a movement, we can understand the ground reaction force, because this is a constant. Mass is a constant. The only things that will fluctuate in this equation are the ground reaction force and the acceleration of the center of mass. This is in reaction to what the person is doing. All right. We only put the force acting on the person into this equation, but we have to do our mental gymnastics and realize that if the person pushes harder or less hard on the ground, this ground reaction force will change based upon what the person's doing. So understanding this is ultimately our goal, to understanding the forces created by the person. All right, so now how do we do that? Well, we go back to our kinematic friends: position, velocity, acceleration, and then we have force, and that's GRF. Sorry, that doesn't look too good, and this should be newtons down here. So now we're going to deal with a PVA setup, and remember, you might want to go back to your kinematics and refresh PVA. All right, position, velocity, acceleration, position, velocity, acceleration, and now we're going to add in the ground reaction force. So now I've got 4 plots, and I'm going to use this worksheet, and I'm going to switch pens here, and I'm going to do the to model the squat down movement that we're talking about. So I've got time on this x-axis, and I'm going to start the person with the center mass at some height. Okay, just envision this is the height of the person. This is 0. This would be probably about 1 meter. And then the person squats downwards, and then the way I've drawn it stays in the squat position. So now they're lower. So on my previous plot, I would say this is time 1 and this was time 2. So now the person's at a lower position over here. Okay, that's them in a low position. That's just a stick figure of them standing still at a high position. Okay, T1 and T2. All right, I'm going to drop these these discrete events down, which indicate the start and the stop of the movement. And if you remember from our PVA, and I'll do this quickly, but this is good information to go back and look at. The slope of the position versus time plot tells us the direction of the velocity vector. In this case, all the slopes are negative. So we have negative velocities. Negative velocities, because we're dealing with vertical movement, indicate downward movement. Positive velocity would be upward movement. We start with 0 velocity and end with 0 velocity. So here's 0 here, and here's 0 here. And what happens is we speed up moving downwards, and then we slow down moving downwards. And that's modeled like this: speeding up moving downwards, slowing down while moving downwards. And we get a velocity plot that looks like this. This is the velocity of the center mass. I'm going to drop a dotted line down at that point there. I'm going to drop these dotted lines down. So all my plots line up. You have a worksheet. You can practice doing these as well. So now I have downward movement, and I have upward movement. Oh, excuse me. This is all down. Sorry. Got ahead of myself. This is downward movement. Speeding up, going down, slowing down, going down. So speeding up, slowing down, going downwards, but all downward movement because all the velocities are negative. All right, now if you remember from your kinematics, the slope of the velocity versus time plot tells us everything we need to know about acceleration. In this region right here, all these slopes are negative, so acceleration will be negative. In this region here, all the slopes are positive, so all these accelerations will be positive. We have 0 slope here, we have 0 slope here, so acceleration will be 0 in the beginning and ending portions. All right, and what happens is the rate of change of velocity starts to increase here, and then the rate of change of velocity starts to decrease. The steepness of the slope increases, and then the steepness of the slope starts to decrease. On this side, the steepness of the slope starts to increase. The steepness of the slope starts to decrease. The rate of change of velocity increases. then decreases. And that looks like this in terms of acceleration. This is telling us how fast velocity is changing. This is the fastest rate of change of velocity downwards while velocity is speeding up. This is the fastest rate of change of velocity downwards while slowing down. Sorry about that. Plot gets messy. Okay. All right. So this is what the acceleration of the center mass looks like during a squat maneuver. You can squat down. Okay. And we're only looking at downward. This is all downward movement. All right. So now we want to go to the ground reaction force. Well, how do we do that? Well, I'm going to just write the equation we derived in the previous page of notes. FGRF equals MACOM plus FG. FG is a constant, and that's body weight. M is a constant, and that is mass of the person. Look at what I can do. I can figure out what my ground reaction force is going to look like if I know my acceleration. And what I will do is I'll take every acceleration point along here, put it into this equation, and then calculate my ground reaction force. So, for example, let me get another piece of paper here. For example, e.g., let's say in this situation, acceleration is equal to 0 meters per second squared. We take this equation, FGRF equals MACOM plus FG. I put in 0, I get FGRF equals FG. Let's go back up to my plot. Here, acceleration is 0. At this moment, anytime acceleration is 0, ground reaction force will be equal to body weight, the force due to gravity. So I'm actually going to go down to my plot here. Let me draw that dotted line down. It's the start of the movement. I'll draw another one over here. And I'll draw this one down as well, just so I can line everything up. So prior to this dotted line, to the left-hand side of this, the ground reaction force is equal to body weight. So I'm going to put a little BW right here for body weight. All right, now let's look ahead and see where else will the ground reaction force be equal to body weight. Well, that will be anywhere where the acceleration is 0, because this equation always tells us when acceleration is 0, the ground reaction force will be equal to the force due to gravity, which is body weight. Fg is body weight, or BW. Okay, Fg is body weight. Okay, so let's look at our plot. Acceleration 0 here, that means ground reaction force has to be equal to body weight. So I'm just going right over here. Acceleration 0 here, ground reaction force is equal to body weight. Okay? So I've got 3 regions sort of figured out right now. I've got to figure out this region and this region. Well, let's go back to our equation. Let's say, for example, let's take this data point right here. And let's say, so this is EG1, this is EG, for example, 2. Let's say, example, A is negative. Doesn't matter what it is. It could be -1 meter per second squared, -0.2 meters per second squared. A is negative. Well, let's look at our equation. FGRF is equal to MACOM plus FG. If A is negative, then this, in order for this equality sign to be true, then FG has to be less than the ground reaction force. Has to be less than. Let me put some numbers in just to show you that. Let's continue with the example, and let's say mass is equal to, let's just round these up to 100 kilograms. It's a person bigger than me, and therefore FG, and technically it should be 980. Well, let me do it just not to be too lazy. FG would be 980 newtons. And let's say A is negative 0.5 meters per second squared. Let's plug these numbers into this equation and calculate FGRF is equal to 100 kilograms times negative 0.5 meters per second squared plus 980 newtons. 100 times 0.5, that's negative 50 kilogram meters per second squared newtons plus 980 newtons. Just following our math, 980 minus 50 is 930 newtons. So FGRF is less than, I'll just write it here, GRF is less than FG. Why? Because A is negative. Anytime acceleration is negative, following our equation, anytime acceleration is negative, FGRF will be less than FG. This is a constant. M is a constant. That is not a constant. This reflects what we see in the movement. So ground reaction force will be less than gravity anytime acceleration is negative. What happens when acceleration is positive? Let's do that. Grab another piece of paper. E.g. number 3, A is positive. Okay, let's do this again. FGRF equals MACOM plus FG. In this case, we're going to do mass is still 100 kilograms. Let's do FG is still 980 newtons. And this time we'll do A is positive 0.5 meters per second squared. Okay, let's put these numbers into this equation. FGRF equals kilograms times positive 0.5 meters per second squared plus 980 newtons, or 50 kilogram meters per second squared, so 50 newtons plus 980 newtons. If I do my math correct, that would be 1,030 newtons is what the ground reaction force will be when acceleration is positive 0.5. Or the more general statement here that I like to talk about is the ground reaction force will be greater in magnitude when, what will be greater in magnitude than the force of gravity, because A is positive. And I'm saying that a little backwards. The forces cause the acceleration. The acceleration does not cause the forces, but in terms of words, this is just a nice way to describe the math. The ground reaction force will be greater than body weight when acceleration is positive. And this is the math that supports that. Okay, so now let's go back to our graph. I've got acceleration that's negative here. I've got accelerations that are positive here. In this region, the ground reaction force will be less than body weight. Sorry. Wow, I need a little bit more coffee. Will be less than body weight. In this region, the ground reaction force will be greater than body weight. And you'll see, because acceleration is the only thing that varies on the right-hand side of the equation, mass and g are constant, our ground reaction force in the vertical direction will look just like our acceleration plot, just offset by mass and body weight. So this line and this line should be parallel. My drawing may not be that great. Ground reaction force is always positive. This is 0 down here. Vertical, this is vertical. Again, vertical, that direction that we're only dealing with. And in this region, the ground reaction force will be less than body weight. In this region, greater than body weight. Why? Because deceleration is positive in this region, acceleration is negative in this region. That is the mathematical explanation. Why is acceleration negative? Because we're speeding up, moving downwards. Why is acceleration positive? Because we're slowing down, moving downwards. And the entire movement is downward. Why is the ground reaction force less than body weight in this region? Because the muscles start to fire less. The muscles start to create less force, and the person starts to move downwards because they're pushing less hard than the force of gravity, and gravity is pulling the person downwards. Why is the ground reaction force greater than body weight in this region? Because the muscles are pushing on the ground at a greater force to stop the downward movement. The bi force is what the person's doing. The ground reaction force is in reaction to what the person's doing. Muscles relax in this region. Muscles fire a lot more in this region to stop with downward movement. Okay, so that's the squat down, and we'll build on this this understanding of using PVA and ground reaction force to look at some other movements. Okay, thank you.